We are recording today's session. There are, like I said, about 164 people registered for this. Most of them probably will not be on the conference. They register because they've learned that I send an email out shortly after I upload the recording to everybody who was registered for the class, and then they come watch the registered one, or the recorded one. But we appreciate you guys participating today. It does make it easier and more lively. And we'll give people a few more minutes before we get started. Oh, here they come.
Absolutely.
So Ed's out. I'm going to speak for Ed for a minute. Ed's out at the Purdue Process Safety and Assurance Center at the University of Purdue in Indiana. If you guys aren't familiar with that, there is a place that has a presence in several parts of the world, from Texas A&M, called the Mary Kay O'Connor Institute, that teaches process safety and gets involved in stuff like that around the world. Purdue Process Safety Center has a bunch, the University of Purdue has a bunch of really smart professors and grad students that are working on some of the science behind what the problems we're trying to solve. And so we have, for lack of a better term, partnered up with them, working closely with them. And they do some research for us, and they crunch numbers for us from time to time. They attest to things that we're doing, and they listen to a lot of what we have to say and a lot of content, looking for ideas of how to make process safety better. And it's a really unique environment, where you basically have an academic environment where people are really focused on solving some really complicated problems to make the world safer for the people who work at chemical plants and refineries and other types of high-risk environments.
Yes. And I will be giving a presentation on a very similar topic. It's so my LOPA didn't work. What do I do now? And this particular one is using fault trees when your LOPA doesn't work. Actually, you could even use that in the quantitative bow tie, because there are situations where independence doesn't exist. And maybe it shouldn't exist, because I mean, you look at your typical fired heater, and a lot of times you're seeing 5 or 6 pressure transmitters on the fuel gas train. And, each one makes sense by itself. And then you look at the whole pile and go, why am I measuring pressure 6 different times here? Is that getting a little bit out of control? And it's because you want your independence to make your risk analysis easy and clean. But if you're using fault trees can handle the fact that I've got a pressure transmitter that's part of the initiating event. It's part of one safeguard. It's part of a second safeguard. It's part of a third safeguard. And the fault tree software will automatically handle that. So I'm doing that at 11 o'clock here at Purdue. I will also be doing it at this coming Global Congress on Process Safety in March. So mark your calendars.
All right. Thank you, Ed. That's awesome. Real quick commercial. You guys obviously know where connexus.com is. You found us because you registered for this conference. There will be another webinar topic showing up later today. And the recorded link for this session will be up in about 48 hours if you want to share it with your friends. It'll probably be up quicker than that, and you'll know about it, but I tell people to wait 48 hours just in case I run into, those unintended things that have to be done. The next webinar that I'll actually be doing in January will be on chemical manufacturing cybersecurity, which has become a really hot topic around the world. Definitely in the United States, we're talking a lot about that. So I'll have that up later today or tomorrow at the latest, and you're more than welcome to log in and watch it. Just to remind you, recorded webinars are available at this link right here under resources. You can register for our newsletter. I would recommend registering for our newsletter. We don't spam you. We don't We send about one newsletter a month. You can read it on your cell phone. It's usually some type of technical article and then an invitation to a webinar. That's it. That's all you get. We don't sell your information. No one else will get it. Actually, I control access to your registration, and I'm very careful that it doesn't get abused. So just a FYI to you. All right. So Ed's going to be talking about Bowtie today. He's going to show you the software, I'm sure. I want to just jump over to the link. We have the same place where all of our cloud-based software runs is also where the Process Safety Training Center runs. So I'm just going to log into it real quick so you can see what this is about. I'm going to sign in as a company employee. I've got a couple of passwords, so the system's always trying to change my passwords, and I'm going to hide everything that isn't a demo. Sorry about that. But just to give you an idea here, I'll jump into my demos. And to start software, like for instance, to do the Bowtie thing, you basically insert a Bowtie application at this point. If you want to do Open PHA and audit, if you want to go into SIS, lifecycle management, things of that nature, firing gas mapping, fault tree analysis is called Arbor. This is where you actually start a project from. If you're in here and you're struggling for some reason, you can pop right into training and browse the available courses. This works for both if your company signs up and wants to basically provide this training to all of its process safety people. Then you can also put your own private courses up here. You'll see that Connexus puts up internal courses. And you can have the same thing. So you can have all of these courses down here that are considered common courses, and then you can actually host your own internal courses too. And there is a metric for checking on how people are doing with the courses that you've assigned and stuff like that. So really useful tool. And that's enough of that. Ed, I'm going to turn it over to you at this point.
All right, very good. Well, let me see if I can get all of this working, because when I travel, I only have my iPad. So I'm much more comfortable doing the webinars from my desk, but let's see if I can share screen, start broadcast, 3, 2, 1. Okay, so you should be looking at my screen, which when I go over to PowerPoint. So tell me, Jim, do you see the PowerPoint deck?
Perfect. Well, we see, yes, we do. I'm sorry. We see the GPS, the conference threw me off.
Yep. All right, so welcome everyone. This is kind of an encore presentation, but better. To a presentation that I originally gave this spring in San Antonio at the Global Congress on Process Safety. The topic is LOPA is obsolete. Move to quantitative bowtie analysis. And the benefit of this webinar is, well, in case you weren't in San Antonio, you're going to get the information. But in San Antonio, in these conferences, you've got 20 minutes to slam through a bunch of slides, and then maybe 5 minutes to answer questions, and we're off to the next topic. So here I'm going to be able to slow things down. I'll be able to take questions. And Jim, please keep your eye on the chat. If someone has questions, feel free to jump in at any time while I'm giving the presentation. So let's start with the title, which is intentionally shocking. Okay, LOPA is obsolete. Oh my God, how could LOPA be obsolete? Everyone.
Hey, Ed.
Yes.
Ed, I'm a little worried. We don't see a slide that says that. We still see the GCPS slide.
Okay, that's weird. Are you seeing a slide now that says presenter?
Yes.
Okay. And how about now? LOPA is obsolete.
Correct. Yep.
Okay. That is strange. I will chalk it up to the quirkiness of trying to do this on an iPad. And please keep track of this. Make sure I don't go off the rails. So yeah, definitely saying LOPA is obsolete, move to quantitative bow tie analysis is deliberately shocking. It's meant to grab your attention. There's nothing wrong with layer of protection analysis. It has a lot of excellent uses. My entire career is almost based on the book that I wrote about LOPA 22-ish years ago now. Um, and if you just have a title like "We're gonna make a few incremental improvements to LOPA," well, there's nothing dramatic about that. All right, so a little bit about me. I'm the president and CEO of Connexus. I got a chemical engineering degree from Ohio State, about 30 years ago now. And I have been on the ISA 84 committee for over 25 years. I was on the committee before the 1996 release. And as a chemical engineer, I focused on process hazards and risk analysis as opposed to the reliability engineering of microelectronics, which there are plenty of other people on the committee to work on. Actually, as of a couple months ago, I am now also on the technical advisory group for SC65, which is the group that puts together the IEC 61511 standard. So a lot of committee involvement, a lot of standards writing in my background. Today, I'm at Purdue, member of the Scientific Advisory Board for P2SAC, Purdue Process Safety and Assurance Center. And I am an author of many books on safety topics, including the big one, Safety Integrity Level Selection, that kind of started it all 22-ish years ago. And then also, Jim and I wrote a book called Security PHA Review, which kind of looks at process plant risks through the lens of your existing hazards and operability studies. I've got a book on fire and gas mapping coming up. It's only about 20% done, but it takes time. All right, overview. Jim, quick status check. You're seeing the overview slide?
Yes, no problem. I
Very
will
good. All right.
interrupt you. I'll interrupt you if we have a problem.
Okay, very good. Okay, so LOPA, it is a ubiquitous process in the process industries. It's done to do process hazards analysis in a little bit more detail, and it's specifically used when you need to be a little bit more quantitative, specifically when you're looking at safeguards that need numerical attributes to them. So if you're looking at a safety instrumented function, which is the archetype, you're going to need to make decisions about architectures, about test intervals, about diagnostics that are going to be required. And those are necessarily done numerically. And layer of protection analysis gives you a little bit more quantification, a little bit more rigor than just a purely qualitative PHA. But LOPA does suffer from some limitations. From the inception, LOPA was intended to be kind of an order of magnitude study as opposed to being something really precise. And it also employs independent protection layers, and it really focuses on preventive independent protection layers when it's making its calculation. So the math is going to end up being really easy, but the math is really easy because you've simplified the situation that you're looking at. Also, in the early days, LOPA was done on a one cause, one consequence basis. And if you're doing something like an SIS design, you really need to be able to aggregate the risk that is posed by a consequence that might be developed as a result of multiple different causes. Also, another limitation of LOPA is that it really can't handle multiple consequences, because when we start looking at mitigation measures like a gas detection system or a fire detection system with a water spray, you get a consequence whether or not the safeguard works. So if the safeguard works, you get a smaller consequence. If the safeguard doesn't work, you have a bigger consequence. But your analysis is not going to be correct until you consider both of those consequences. That's another thing we need um, to overcome in order to accurately assess the risk in a wider set of situations. Now, all of this is the result of something that I've been doing for a few years, almost a decade now, called unified hazard assessment. And this is the result of academic research. This is the result of project work. This is the result of developing software, in that there are a lot of different risk analysis techniques. And those different techniques have different specific uses where they're very valuable. But the underlying data structure for how risk is presented, how the studies are presented, it's not too difficult to try to develop an underpinning data structure that's going to allow you to do your risk analysis in multiple different ways, whether you're doing a bow tie or a LOPA or a HAZOP or even fault trees. You can look at the data that sits underneath the risk analysis in a standardized way and then flip switches to say, okay, I want to look at this data as a HAZOP worksheet, or I want to look at it as a hazard register. So that's what we're doing in quantitative bow tie, is a part of that unified hazard assessment. And ultimately, what you're going to see in this presentation is that quantitative bow tie analysis is taking LOPA. LOPA is kind of the starting point, and stretching it out a little bit to address some of those LOPA shortcomings. Now, progression of risk analysis. So in order to explain the value of what we're doing with quantitative bow ties, we're going to go back to the beginning and work our way up to quantitative bow tie by stating, okay, this is where we started, this is what was wrong, this is how we fixed it. And we keep building up into the quantitative bow tie. So in the beginning, there was HAZOP. Actually, there wasn't HAZOP in the beginning. HAZOP is not even as old as I am. Kind of the formal structured brainstorming analysis of risk didn't happen until the 70s, whereas I happened in the 60s, the end of the 60s. But prior to HAZOP, when process plants were designed, the safety analysis was kind of limited to just looking at the P&IDs and using expert judgment. So, oh, sorry about that. And HAZOP was good when we developed, because now, instead of just using judgment, we're going to formally look at the risk of the plant by postulating things that can go wrong. Can I get a high temperature? Can I get a low pressure? And I'm going to develop the causes of that scenario and the safeguards and make a qualitative judgment as to whether or not the risk is okay, or whether something needs to be done about it. And as we started going through the HAZOP process, we started to notice that, well, we're getting different answers from different teams because risk isn't being judged properly. And people first started to notice what I call the binary of risk studies. And by binary, what I mean is, depending on who the team is, the risk of the scenario, or the consequence, or the likelihood of the scenario, is either all or nothing. If this consequence has happened to me or in my plant, it happens all the time. But if it hasn't happened to me, or it hasn't happened in my plant, it will never happen. It's inconceivable. So LOPA extended HAZOP to help us better quantify the frequency. It doesn't do anything to improve the consequence assessment. We're really looking at frequency. So it's going to allow you to look in a way that you can get a better grasp on what's going. So instead of asking the question, how often is the plant going to blow up, which nobody knows, you're going to ask smaller questions like, how often does this pump fail? How often will an operator not be able to bring the process to a safe state? How often will this control loop fail? And those smaller questions are more easily and more consistently answerable. And then the local process just gives you a mathematical framework to kind of string those things together. But as we started developing LOPA, it was a quantum improvement, and for the last 20 years or so, it's been expanding, it's been improving. People are making changes, but we're starting to get caught still. One of the problems that we'll talk about is that in LOPA, you've got a worksheet presentation. And if you're doing what we call an explicit LOPA, so you're actually calculating frequencies and comparing them against target maximum event likelihoods, you start to lose visual thinkers. You start to lose non-technical people who just kind of look at a screen full of numbers and their eyes glaze over. So one of the first and primary benefits of the bow tie diagrams is that it's going to help visual thinkers and non-technical peoples, like your maintenance people, your management, are going to be able to look at a scenario graphically, and it's going to have more of an impact than just rows and rows and rows of numbers. So this bow tie diagram, as it is done today, so there are a lot of bow tie software applications that are already out there that are simply drawing a picture. And as a matter of fact, I would argue that most bow tie diagrams today are done using PowerPoint or Visio. And right now, the state of bow tie diagrams is that they're primarily used only for important high consequence scenarios, and they're used to communicate the risk of those high consequence scenarios to a variety of stakeholders. Matter of fact, right now I'm working with a rather large company, or a couple of large companies in France, and their process safety regulator is requiring the process plants that operate in France to present their high consequence scenarios in bow tie diagrams, where they explicitly can see all of the causes, all of the consequences, and all the barriers that are being credited, so that they can follow up and make sure that those barriers are designed properly and being maintained properly. Now, if you look at a typical bow tie diagram like you see on the screen here, you're going to see it reads from left to right, and it kind of looks like a bow tie because it's big on the ends, and it all necks down into a knot in the middle. Now, the way things work is you're logically moving from left to right. And on the left, you're going to have threats, or in the language of LOPA, we call them initiating events. In the language of HAZOP, they're called causes. Again, another case for a unified hazard assessment, because the same thing has different names depending on what drawing you're looking at. So causes on the left. And then for each cause, there are barriers, which are safeguards or independent protection layers. If a barrier is on the left, that means it's a preventive barrier. So if I have an initiating event with a preventive barrier, and that preventive barrier is successful, that's where the scenario ends. Now, the middle or the bow tie knot is the hazardous event being prevented. Sometimes they will call it a hazard. I like to be a little bit more careful with the term hazard because it's got 20 different definitions depending on what industry you're in, what risk analysis method you're talking about. But the way bow tie diagrams are typically done in the process industries, and what I would recommend, is that the bow tie knot is the loss of containment. When you get there, the material has gotten out of the pipe. And as you can see, that loss of containment event can happen as the result of multiple different causes or threats. And each one of those causes or threats are going to have potentially the same or potentially different preventive safeguards or preventive barriers that will prevent the loss of containment. On the right-hand side is everything that happens after you lose containment. There are going to be not just one consequence, but the potential for multiple different consequences. So when you lose containment, there could be a fire, there could be an explosion, there could be a toxic gas release. And the magnitude and type of the consequence can be manipulated by the mitigative barriers. So mitigative barriers are those barriers or those safeguards that are going to act after you've lost containment that will modify the consequence. Generally, what we're trying to do with the mitigative barriers is make the consequences smaller. So this is a typical bow tie diagram that you may or may not have seen. They are extremely common, actually. And what you're looking at is what you typically see in a bow tie diagram. It's just a pretty picture that helps to explain the scenario and give it a visual impact. But what we're going to do is we're going to go a little bit further, and we're going to say, well, since we built this diagram, why don't we just throw some numbers on top of it and make things a little bit more useful, shall we say. Now, also, what I didn't show on the other diagram is that bow tie diagrams also have things called degradation factors. So in this figure, you'll see that I have a potential preventive barrier or an independent protection layer that is called separator vessel high level closes the inlet valve. UZC 11 is my safety function. It's a preventive barrier against the level control loop failure that's going to cause overfill in the vessel. Now, we know that safeguards can fail. They might not work for a variety of reasons. So the bow tie diagrams are going to allow you to look at degradation measures and also control of the degradation. So you'll see for that safety function that it can be put into a degraded state because the safety function got left in bypass. And then you'll also see kind of the drop down on the way back to that safeguard is a degradation control measure, which says, okay, well, bypass is a bad thing, but we can control bypass through our bypass control management system. So again, kind of, it's not quantitative in nature, but it gives you a larger explanation of what are all the things that can go wrong and what are all the measures that we're taking to control those things that can go wrong. Another big benefit of the bow tie diagram. Okay, so now let's go back and look at LOPA. So what you're seeing is a worksheet out of the LOPA purple book that was released roughly the same time as the LOPA book that I wrote. I was actually done with mine first, but don't get me started. Don't get me started on my co-author. Okay, so this worksheet, I went and I did a scenario in the worksheet in the LOPA book, and the scenario was related to a feed pump seal failure. So you look at this worksheet that's available in the book. You could download umpteen thousand spreadsheets that will have one scenario per page, and you'll see that it includes all the stuff. What is the consequence? what is the tolerability criteria of that consequence? In this case, it's 1e minus 3, so it's quantitative. What is the initiating event that causes the consequence? And then it looks at the variety of safeguarding, including enabling events, conditional modifiers, which I'll talk about conditional modifiers a little bit more in a second, and the independent protection layer. So in this case, the only independent protection layer was a safety instrumented function that was given a probability of failure of 0.1, and we calculated a risk gap of 10. So this was kind of state of the art, one sheet of paper, and we had one cause, one consequence. And people were happy with it, but we started running into problems pretty quickly. The first thing that we said is, man, I can't have one full sheet of paper for each LOPA scenario. My library doesn't have enough space to do that. So we started putting LOPA scenarios into a spreadsheet format. And what you're seeing here is the Connexus Open PHA product, where you're looking at a LOPA worksheet. So we did exactly the same thing as the previous exercise, but we put it into a worksheet format. It's a little bit more compact. It's a little bit easier to read, but it tells you the same thing. What is the cause? What is its frequency? What is the consequence? What's the tolerability of that consequence? What are the independent protection layers? And then a calculation of whether or not risk is tolerable. In this case, it's not, because this scenario still needs a risk reduction factor of 10 to make risk tolerable. Okay, so on the previous two slides, we did a calculation of the frequency of the unmitigated event. How did we do that? Well, this is where LOPA is strong and weak at the same time, because it has a mathematical underpinning, because we're going to look at frequencies, we're going to look at probabilities, and we're going to combine them based on the logic. So if you have a logical and, you're going to use probability multiplication, multiply everything together. This is going to be the relationship between the initiating event and the independent protection layers. So in order to have a consequence, we're going to look at the initiating event frequency and multiply it by the probability of the failure of the independent protection layers, because in order for a consequence to occur, you have a logical and. I have to have the initiating event and failure of protection layer 1 and failure of protection layer 2, and so on. That's why you use the probability multiplication. Probability addition, simply adding probabilities together, adding frequencies together, is how multiple initiating events are going to be related. And I'm going to show you that on the next slide, because we came to the conclusion real quick that in a lot of situations, there are multiple causes that are interrelated, and we need to look at a summary risk as opposed to risk one cause at a time. And you combine them by adding, because it's a logical or. I will have a consequence if initiating event 1 occurs, or if initiating event 2 occurs, or if initiating event 3 occurs, and so on. So that's the mathematical underpinning of the layer protection analysis. So if I take that same scenario, and instead of only looking at one cause, I look at multiple causes, the worksheet starts to look like this now. So I'm going to have low flow is my deviation. I'm going to have a consequence of loss of flow. It's going to result in seal failure, ignition. Everything in the first 4 columns is exactly the same as it was before. But once you get to the cause column, you'll see that there are 3 different things that can cause that seal failure. So discharge control valve failing to the closed position, loss of liquid in the supply vessel, inadvertent closure of manual valves. And each one of those causes has its own frequency, sorry about that, and its own independent protection layers that will work against that cause. So in the case, for instance, of loss of liquid in the supply vessel, we have the low flow shutdown, but we also have operator intervention based on a low level alarm. And when we're running our math in our LOPA, for each one of these cause rows, we multiply the frequency times the PFD of the protection layers. And then we add together the frequencies of the additional rows, and that's where we get this number MEL safety, mitigated event likelihood. All right, so that's what everything looks like on a LOPA worksheet. And so far, we're still fine with layer protection analysis. It's giving us the answer, but now we're going to take the data and we're going to present it as a bow tie diagram to help people visually look at it. So this worksheet in OpenPHA and this worksheet in bow tie have the same exact information. They run the same exact calculations. So you have the three causes on the left. For each cause, you have its preventive safeguards. And each one of the causes you'll see has a frequency associated with it. Each one of the preventive barriers has a probability of failure on demand associated with it. And you're seeing a little bit more detail because the software here is then going to calculate the frequency of each of the cause rows, considering the cause and the preventive safeguards, and then add them together to tell you the frequency of the loss of containment event. And this is kind of where the LOPA stops. The LOPA calculate, so the bow tie is calculating 1.2 E minus 2. If you look at the LOPA worksheet, it calculated 1.2 E minus 2. Everything is exactly the same. And also you'll see that the consequence that we listed and gave a target maximum event likelihood of 1 E minus 3, that's why you're going to see that red light down there, because for that consequence, the acceptable frequency and the calculated frequency don't mesh up. We need the calculated frequency to be less than what is tolerable, and that's not the case. So this is kind of a starting point of, we just took, a standard run-of-the-mill LOPA that people have been doing for 20 years and just drew it in a different format to help people think about it a little easier, look at it a little easier. But, there's not a compelling case yet, because I can assure you that it's a lot more work to enter this information in this graphical format than it was to just enter the information into the worksheet. Luckily, there are software tools where you could just press a button and it's going to dump the data from here into there to make your life a little easier if all you need to do is present the information. But now that we have this framework set up, we can expand on it and start doing other things that a traditional LOPA can't do. So now, in this exercise, I didn't look at conditional modifiers, which for this scenario are actually important. If you have a failure of a pump seal on a pump that is pumping flammable material, you don't necessarily have a consequence after loss of containment. You won't have a consequence unless the area is occupied and unless the release is ignited. So those things like probability of ignition, probability of occupancy have long been handled in LOPAs as conditional modifiers. So let's take a look at these conditional modifiers in the quantitative bow tie framework. So if I was only going to do what you see in a LOPA, I would put the probability of ignition in as a mitigative safeguard on the right-hand side of the bow tie diagram, as you see here. So right now I've got a safeguard called ignition control program failure causing ignition, and I gave it a 30% probability of ignition. So that modifies the frequency. That changed the frequency from 1.2 E minus 3 to 3.6 E minus 3. But what you're looking at here is appropriate for a flammable material, but it might not be appropriate for something that even if the material doesn't ignite, you still have a consequence. So in this case, and the way that LOPA typically handles those conditional modifiers is that if the condition is false, so there's no ignition or no occupancy, that also means that there is no consequence. The power that we're going to start seeing in quantitative bow tie is, well, what if there's a one consequence if it ignites and a different consequence if it doesn't ignite, but both of them are bad and both of them need to be limited. That's where we're going to start seeing value, because quantitative bow tie gives you the ability to handle multiple different consequences. So now I'm looking at, instead of a pump with gasoline, now maybe I have a pump that's pumping liquid ammonia. And with the liquid ammonia, ammonia does burn. Usually doesn't, but it can burn. So now, if you look at the top row, actually the liquid ammonia might kind of confuse the issue. So another example that might bring this home for you a little bit better would be if you were releasing sour gasoline. So your gasoline has an appreciable amount of hydrogen sulfide in it that's going to cause an H2S gas cloud. So if you think about it that way, if I get a release of the gasoline and I get immediate ignition, I'm going to get a pool fire. I'm going to get a potential hospitalization injury. And that is tolerable, that we said, at 1E-3. But if it doesn't ignite, I'm going to get a toxic gas cloud. And that toxic gas cloud could cause a single fatality injury. So now what you're seeing is a mechanism to look at the fact that I have some safeguards on the right-hand side of the bow tie that, whether they work or not, there is going to be a consequence that I need to manage. And they're different consequences. They might be managed different ways, but my risk is not tolerable until both of those consequences are tolerable, not one or the other. Now, some of you that have a lot of expertise are probably saying to yourself, oh, well, I don't need a quantitative bow tie to address that. I can use multiple LOPA scenarios. So I can have one scenario where the consequence is pool fire. I can have another scenario where the consequence is toxic gas cloud. And I can kind of look at the consequences and make sure that they're the same separately. Absolutely. What you're saying is absolutely true. It's just that when we're moving into the quantitative bow tie diagram, now we're also getting the benefit of the visual view, the visual nature of the presentation of the risk information. Okay, now when I'm handling mitigative safeguards, which is the big benefit, you're probably catching, that's the big benefit of the quantitative bow tie over the LOPA, is that mitigative safeguards reduce the consequence, but they don't prevent it. So whether or not the safeguard works, there's a consequence. If it works, the consequence hopefully will be small. If it doesn't work, then the consequence is going to be big. Now, historically, you've got some options for how you deal with it. And the most common one is the first option on the bullet list. Okay, well, I have a gas detection system that some of the time isn't going to detect the gas cloud because I don't have an infinite number of detectors. Even if it does detect the gas cloud, it might not be able to do anything about it before the ignition occurs. So you know what? I don't believe it's going to give me a 90% prevention. So I'm just going to ignore it. So right now, a lot of times, and this is if you've been a facilitator and the team says, I want to take credit for this gas detection system, and you have to tell them no, this is not a fun conversation to have, because they're all saying, well, if we're not going to take credit for the gas detection system, why do we have it? Well, you can take credit for it, but it's more complicated, and a traditional LOPA doesn't allow it. The other thing that we can do, which you'll see a lot with things like diking around tanks, is to assume that if the safeguard works, there is no consequence. So if my gas detection goes into the alarm state, no explosion is going to happen. So ignoring the safeguard is a little bit excessively pessimistic. Ignoring the consequence when the safeguard is effective is a little bit, it goes the other direction, and it's a little bit on the aggressive side, on the risk-taking side. And as I already mentioned, you do have the third option to just kludge together a whole bunch of LOPA scenarios, one for each consequence, and you should be able to get to roughly the same place. So now, looking at that concept a little bit more, let me look at a quantitative bow tie of tank diking. So my scenario is a tank overfill that could result in a pool fire. The cause is control loop failure at 0.1 per year. And we have a preventive protection layer, which is the high level shutdown. If the high level shutdown works, there is no overfill. We put in a SIL2 system, gives me a PFD of 0.01. So the frequency of overfill is 1E minus 3. That's the frequency that we get to the knot. And then once we get to the knot, we can go in two different directions, because we're going to look at the mitigative safeguard of the containment dike. So for the containment dike, whether it works or not, so there's one situation where all the material is contained in the dike, and then there's another situation where the dike ruptures and you spill the material out. So if it's contained, we have a small pool that is still capable of igniting and having a fire. And if the dike fails, we have a large pool. And if it ignites, now we're going to have a very large fire and a different consequence. So if you look at the consequences all the way on the right, you'll see that if the dike works, you're going to get a small pool fire that's tolerable at 10 to the minus 3. But if the dike fails, you're going to get a large uncontained fire that's only tolerable at 1 times 10 to the minus 4. And we put a probability of failure as per the LOPA IPL book of 0.01 on the failure of the diking. And once we did that, we were able to demonstrate that the tolerability of the small consequence is achieved and the tolerability of the large consequence is achieved. So again, this is kind of shows you the strength of the quantitative bow tie, in that we're doing a LOPA calculation plus, because now we're able to look at multiple different consequences, multiple different initiating events, all in one framework. Now, the biggest reason that we got into this, that we started talking about this, is because Conexus does a lot of work on fire and gas systems. And the design of fire and gas systems gets a little bit tricky because it is a consequence mitigation measure. And when you look at a fire and gas system, there are a lot of things that can make it go wrong. What you're looking at is from the technical report from ISA 84.00.07, which basically gives you the litany of things that can go wrong with the fire and gas system that will prevent it from doing the mitigation that you're hoping for. We call the combination of these three things the fire and gas system effectiveness. So in the fire and gas system, the first thing is coverage. So what is the probability that I have a gas detector in a location that it's actually going to detect the gas cloud, given the fact that I've got a wide range of release sizes and my wind direction and wind speed can be all over the place? So what percentage of the time will my detector be in the right location? The middle column is safety availability. That's your traditional SIL from safety instrumented systems, the probability of failure on demand of the electronics. So even if the detector's in the right spot, if it's not working, you're not going to get your mitigation. And then finally, you have your mitigation effectiveness. So I have a detector in the right location to detect the fire. The detector works, it signals to the fire and gas system to turn on the water deluge. And we turn on the water deluge, but it doesn't put the fire out. That's the mitigation effectiveness. Did the action that you took to mitigate the fire put it out? Maybe your water spray was not sufficient for the fire size you have. Maybe your Novec canisters didn't work because somebody left the door open and all your Novec shot into the hall instead of putting the fire out. That's what we're talking about in that mitigation effectiveness column. Now, what we're proposing to do is this is the type of thing that can be handled in a quantitative bow tie. So you would need to calculate all these parameters. So for a case study, one second. Yeah. So I've got a case study where I have a bullet. So think of the tragedy. Well, it's not. I wouldn't call it a tragedy because there weren't any fatalities, but the accident that occurred at PES a couple years ago, Philadelphia Energy Solutions, where they had a very large butane or propane. I think it was butane vessel in their HF alkylation unit. So picture that scenario. I've got a liquefied petroleum gas and I want to design a fire detection system to make risk tolerable. So you'll need to calculate probability of failure on demand using all your SIL verification software and techniques. Your mitigation effectiveness, good luck trying to figure that out. We try to design our mitigation so that it works, but we can look at some historical data to see what the probability it is that it won't, simply due to human failures. And then that last calculation of the coverage is something that we can calculate in our effigy software. So what you're looking at here would be the fire detector coverage of a couple of butane bullets. The software calculates the graphical display that you're looking at there. Everything that's green is covered by 2 detectors. If it's yellow, it's covered by 1 detector. If it's red, that means no detectors can see that location. So we use that type of analysis to determine what the probability of being able to detect a fire is. In this case, the coverage is going to be pretty high because the size of the fire is going to be very large. If we're talking about a pool fire of butane. So now if I look at that scenario in a quantitative bow tie, and I apologize, it's going to be a little bit hard to see the writing. This is something that I'm working with my software developers to figure out if there's any way to make these things easier to read. Granted, there's a lot of information being presented, but there's also a lot of white space. You'll be the first to know if we come up with a way to make these easier to read. So in this case, the cause is that I have a leak from the butane bullets or any associated piping. Right out of the gate, this situation is almost impossible to handle with LOPA. If your initiating event is the loss of containment, what do? You either have to change the initiating event frequency or you have to deal with mitigative safeguards. And dealing with mitigative safeguards is what we do. So you'll see that the butane bullet leak is what we're worried about. If it ignites, we have a potential for a fire. We have a potential for a vapor cloud explosion, and we have a potential for the worst case, which is going to be that Blevy fireball. But we have mitigative measures that can reduce the risk. So first off, our ignition control program. There's no guarantee that even if something is released, it's going to ignite. So if you look at that top consequence, I'm going to have a release of butane, but it doesn't ignite. So there's no significant safety consequence, just kind of environmental cleanup and lost production. So also on that consequence one, you'll see that there are 3 different categories, one for safety, one for environmental, one for asset, each having its own target maximum event likelihood. Everything is green lit at the moment for consequence 1. Then we have consequences 2 and 3. And consequences 2 and 3 will occur when the ignition control program fails and there's an ignition. Now, the middle row is the you get an ignition, but the fire detection works. The deluge works, and you're able to not put the fire out, but keep that vessel cool enough so that it doesn't levy before you're able to put the fire out. So we've in the middle row, we're going to get a large semi-contained pool fire that doesn't result in a levy because our fire detection system was capable of detecting it and putting the deluge on. The bottom row is where the levy occurred because the fire you had an ignition and the fire detection and deluge function wasn't sufficient to prevent the levy. And again, that fire detection protection layer, it needs to consider all 3 of those components. Do you have detectors in the right place to detect that the situation is occurring? Do they work? Have the devices not failed? And if everything works and that safety function activates, what's the probability that you're actually going to be able to get to the safe state after you've done the deluge or after you've activated the dry chemicals? All of that goes into that probability of failure on demand that you see there for safeguard 3 and its complement, which is called safeguard 4. Okay, so that's kind of hitting one of the most valuable use cases of the quantitative bow tie, which is looking at scenarios that only have mitigative safeguards, such as fire and gas detection and suppression systems. All right, so in conclusion, LOPA is ubiquitous, but it must be extended to meet the full range of required applications and use cases. If you take your LOPA and you extend it out to a quantitative bow tie can do everything that a LOPA can do, but it's going to expand to where you're going to be able to look at multiple different consequence outcomes inside the same scenario, inside the same framework in one drawing. The quantitative bow tie is going to give you an elegant calculation of effectiveness of mitigative safeguards, and it's going to give you that beautiful visual representation of the risk scenario that's going to be able to help you communicate to the wide variety of stakeholders in the risk, some of whom are not engineers that love spreadsheets full of numbers and would prefer to look at a diagram that helps them almost feel the risk scenario as opposed to just intuiting it by looking at the numbers. So with that, that is all I have for the presentation. Can you believe that I was able to give this presentation in under 20 minutes back in San Antonio? All right, so with that, let me turn this back over to Jim. Jim, did we get any questions in the chat before we open up the floor to other questions if you haven't asked one yet?
Yeah, actually, we did not. The chat box is empty.
Okay. You know, say, hey, I get stunned silence quite a bit. But yeah, this is I really love the format of the quantitative bow tie to address multiple consequence scenarios, mitigative consequences. But even quantitative bow tie is going to suffer the situation that I'm going to be talking about at P2SAC today, which is in order for that structure to work, everything has to be physically and functionally independent. And if my alarm protection layer and my BPCS protection layer and my SIS protection layer are all using the same 2 out of 3 voting set of transmitters, Quantitative Bowtie and LOPA can't handle that, but fault tree analysis can. Hold on 1 second.
Hey, Mario, if you have your hand up, go ahead and turn your mic on. And
okay, sorry, it's because I didn't have the time to type out my question, but basically, sure. From what I've seen is that right now you are starting your bow tie by filling up the spreadsheet, right? Or can we start up that bow tie directly on the graphic and have the one initiating event?
No, you can. We have the software that we're looking at, and I deliberately didn't make this a software sales pitch. This is all theory and technology. But in our software, it works almost like if you've ever used fault tree software. When you open the software up, all you're going to see is a top event. And then you'll press the plus button right there, and it will add causes every time you press the plus button. And when you press this plus button on a cause, it will add more safeguards, and it will allow you to not only add new safeguards, but add additional instances of existing safeguards. So you'll see this low flow shutdown appears for all 3 causes, but in the database, it's only one safeguard, one entry in the database. So all of this can be built out directly in the Bowtie software. You don't need to start with the local worksheet.
Okay, so yeah, Ewald asked a question: do you have to consider multiple failures of mitigating barriers?
Do you need to consider multiple failures of mitigating barriers? Okay, so
here's Ewald. Maybe I can explain. If you have 2 mitigating barriers in one sequence in series, isn't that a double failure scenario, or do you even expect 2 or 3 in series to fail at the same time?
Yeah, you can. So let me go back here. So in this bow tie, you'll see that there are 2 mitigations on the way to consequences 2 and 3. One is related to ignition. One is related to the probability of failure of the fire and gas system. But if you had like 2 true mitigative safeguards, so you have a dike and you have a firewall and you have a fire and gas system, you can list all of those different mitigative safeguards on the way to a consequence. So what you need to do is define what the consequences are, the full range of consequences that you're concerned about, and what mitigative safeguards are available that are going to change what the consequence is. But what this does not do, the right side of the bow tie often is described as an event tree. What you're looking at isn't exactly an event tree, because in an event tree, we'll be kind of taking each mitigation one at a time and creating multiple different rows, so that if you look at a typical event tree, you can have the same consequence show up in multiple different locations. So when you're doing the quantitative bow tie, you kind of make a list of what your consequences are and then put the mitigative barriers in. But you can have many mitigative barriers.
All right,
Okay,
so
thanks. I've never had a look from this point of view. Thank you.
Oh yeah, I mean it's going to take some time for people to get used to start using it. We're still in the beta phase on our software, so we just finished up some beta testing with a couple of larger international companies, and we'll be doing some updates soon. But yeah, people are kind of just still getting their hands around it at the moment.
okay, and another question was, is it possible to build directly in Bowtie, or do we first need to fill up a spreadsheet? And I think you've already answered that one.
Yes, I have. Absolutely. Build direct.
Mr. Gonzalez, I do see your hand up. I'll get to you in just a second. Jana asked, LOPA and event tree analysis together is Bowtie. Is there any mandatory requirement for any regulators to use Bowtie? You mentioned in France it is mandatory to use Bowtie. Any other country?
Not that I'm aware of. The only place that I've seen it is in France. But you know, I wouldn't write it off happening in Europe first as a whole, and then maybe working its way to the US. The US is generally a little bit against adding things into the regulatory mix, but I could see it happening across Europe as a whole.
Yeah, let's not take a negative away from that, because regardless of the regulators, it's still a very valuable tool for explaining not only what's actually going on and understanding it across the board. I didn't come from the process safety industry. I came from the automation industry, and my background is physics, not chemistry. So when I look at this, it makes perfect sense to me. Whereas when I look at what's done in LOPA and event trees, I understand because it's basically Boolean logic type ideas. But LOPA sometimes is very confusing to me. So if you're arguing with management that didn't come up out of the process safety world, that you need money to do a project, this is actually a very valuable tool to convince them of why.
Yeah.
James asked a question about if we mitigate highest severe consequence, then the rest becomes mitigated. As in the case of tank overfill, dike failure, then is there any difference in LOPA or Bowtie?
Okay, so actually, it's good that I landed here on this diagram, because what you'll see is, and I did this deliberately, I generated a scenario. The worst consequence by far is the BLEVE. And you'll see, if you go down to consequence 3, all of the frequencies have green lights, meaning the consequence of the worst case is acceptable. But the consequence of the medium case is not. So there's your fire and gas system allowed you to make the potential that we have a BLEVE tolerable, but just the fact that I have a large pool fire is not tolerable. And there's nothing that the fire and gas system, to be honest, is going to be able to do to mitigate consequence number 2 back to acceptability. So with some of these consequence mitigation measures, the mitigated risk might be okay, but the unmitigated risk might be okay, that worst case consequence. But you know, a lot of times that consequence that is still present even when the mitigated barrier works is not tolerable. And that's your sign that says, I can't get out of this box with consequence mitigation. I need to go look at initiating event frequency. I need to go look at preventive protection layers.
Lilia, I apologize. I couldn't see your whole name in the chat box.
It's okay, don't worry.
So I assumed you were Mr. at one point. I apologize for that. So Ms.
No,
Gonzalez.
it's okay. Yes, don't worry about that. Ed, first of all, thanks for all the information. It's very interesting. I have two one is a question, another one is like a recommendation that you can give us. Okay. I am not very familiar with bow ties. We never use bow ties. We are in the old era using lopa. Okay. And the thing is that if you have anything or any book or publication that you can recommend in order to learn about how to prepare these bow ties. I know that there are softwares and all the thing, but uh, suppose that I don't have the um, accessibility for softwares, but
Yeah.
I can buy whatever book that I will need in order to learn about this technology, this new way of calculate risks.
Sure.
And the other
Go
one
ahead. Go ahead.
is, sorry, and the other one is um, in IIC 61511, in the life cycle, we have the risk analysis. It's not totally um, said that we need to use a HACCP and we need to use the LOPA, but in the attachments of the IIC 61511, the part number 3, the only references that they made is the graphic one and the LOPA. What do you believe that is going to happen with IIC 61511 once all these quantitative Bowtie is established? We're going to
Okay.
have another review?
Well, all right. So I don't think. Let me start with the second part first, then I'll backtrack to the
Okay.
first part. The use of quantitative bow tie is simply an extension. So a lot of the discussion in part 3 of the 61511 standard related to LOPA is applicable to using quantitative bow tie. It's just there might be a need for an extension of the LOPA discussion to talk about multiple consequence scenarios and how you can use quantitative bow tie to address those mitigative safeguards. But that being said, a lot of the time when you're designing safety instrumented systems, they are preventive. And for a
Yes.
preventive system that only has one consequence, your layer of protection analysis, standard layer of protection analysis, much of the time works just fine. Okay, so and then going back, software. We have software which makes pretty drawings. It's makes life easy to use. But I showed you the theory of what's going on here, and there's no reason this bow tie that you're looking at here, there's no reason that you couldn't have done exactly the same thing in a spreadsheet. It's just that you would have to type in the equations in the field yourself to run the calculation. So there's nothing magical about software. Anything that you see in this presentation on these slides, you could have done just as easily in a spreadsheet. So what do I need to do to make this more accessible? Well, I just put together this presentation earlier this year. Our software is still in beta, so there is work that needs to be done. So I have another book in the works called Unified Hazard Assessment that will give a more thorough description of quantitative bow tie, the underpinning calculations, and kind of give some examples of how to run the calculations by hand and in spreadsheets. That's coming up. Maybe 2023 will be the year that I get that out.
Okay, and those are the only literature that you recommend to look at.
CCPS has a book on bow tie, but it's only drawing the pictures. There's no quantification underneath in the current book from CCPS.
Yeah, yeah, because I work in a company that is a consultant company. I am QB certified engineer, and I had to work a lot with a Vale, that is a mining company named Vale. They have their own standards and all the thing. And normally, when they ask for the functional safety cycle, they ask to use the bow ties. And the way that they explain the bow ties is very confusing. Okay.
Yeah.
And then the time that I had to do the thing, it was a very hard time to me. And I did it, but I didn't understand it.
Okay.
And that is the worst thing to do if you do the things that you don't understand. Okay.
I agree completely. And there is quantitative bow tie has not been documented in the literature as much as it needs to be. And I will do my best to contribute to taking care of that problem.
Yes, I will appreciate that thing because
Right.
I am very passionate about all this functional safety.
All right. Okay,
Yeah,
well, Jim, I have to put my shoes on and head to the other side of campus because I've got another presentation in 45 minutes and I have to walk there. So I will let you go ahead and wrap with everyone if that's all right with you.
Yeah, no, it's fine. I actually answered the questions in the chat boxes. So thank you very much, Ed. I appreciate it and enjoy the conference.
All right. Thank you. Will do. Thanks, everyone. I really appreciate your
Thank you. Thank you so much. Bye-bye.
A couple other, as you guys are all bailing out, a couple other answers that may be of interest is that one of the questions that came up was about access to things like failure data and stuff. When you use, we have a version of PHA software that you can download called OpenPHA Desktop. You can actually download that from our website at no cost. That doesn't have direct access to our failure database or anything, not like you need it at that point. But when you go to the OpenPHA cloud and all the other cloud-based software products, including this product, this does run in the cloud. What that means in essence is it's running on a server that we lease from Microsoft, which we use their security and our security on. And then you have access to our entire database of failure data and all that information that you need when you're trying to do this type of work. I do it from time to time just to try to remember how to do it, but it's not my day-to-day job. But yeah, when you use any of our cloud-based software, you have access to that database. The Unified Hazard Assessment that Ed mentioned, it long-term is going to drive more integration. Not only have we integrated training with our software products, but we also have the ability to export and import certain pieces of data or information from other software products to other ones inside of the cloud. And that's going to get much more extensive. Last thing I'll leave you with is when you work in our system, we wrote everything in a very readable language called JSON. Deliberately, if you're not familiar with that, please look it up. It's JSON. It is a natural language programming language. It's very easy to do reports out of and things like that. So reports are as easy as using pretty much plain English wildcards. And so it makes it very easy for programmers at your company that are running maybe a dashboard for the company to actually record or to do reports, centralized reports, if you will, of information, things like that. We provide dashboards in our cloud, but we also wrote our product knowing that we may not always be the best solution. Other people might be better. So we don't lock your data up in a way that you can't use it, that you can't export it, that you can't move it from our platform to another platform. So just a FYI about our philosophy, if you will, about software and about our services and the fact that we do software services and training. We are completely an open hand company. So if you're not familiar with that, we don't approach our customers with our hand closed, holding information or knowledge or something else in it or your information. Everything is open-handed. And so our approach is basically, look, you want to work with us, work with us. You don't want to work with us, it's not a problem. You work with us for a while, you decide you want to move to another platform. We may not always be the best solution. We know that. So if you want to move to another platform, it's easy to move your data. All right. So with that, I'm going to close it out. And what we will do is I will post the recording later. It's really interesting. We ended up with about 45 or 46 at the maximum people, which is about what I guessed for a registration of 160 plus. And what's really funny is I will actually publish this later today if I can. And within about a week, all the rest of them usually watch it. So you're more than welcome to register anytime. And the chemical manufacturing cybersecurity information will be up later today or tomorrow about the next webinar in January. All right. Thanks, everybody. I appreciate your time and have a wonderful, blessed day or evening.
You too. Bye.
Thank you.
Bye, guys.
Thank you. Thank you.